Okay, so we are going to do Dirac delta potential, a problem from quantum mechanics, and the one-dimensional potential problems. We are going to do today Dirac delta potential. Okay, so you must be aware with the Dirac delta function, and the Dirac delta function is a function which suggests that there is a distribution or that there is a contribution at only a single point, and for all other points you don't have any contributions. For example, if I set a point charge like object, then you have this kind of representation to define your point charge or point mass. Today we are going to discuss something called as Dirac delta potential. Okay, since so this is a problem in one-dimensional problems in quantum mechanics. So we are going ahead with that particular topic. So like this is your Dirac delta function. So I'm redefining my Dirac delta function here so that you may remember all these things. You must remember all these things. Okay, so this is 0, this is infinite at x equal to 0. Okay, now let us consider in first a very simple case of attractive Dirac delta potential. So we are considering the case of attractive Dirac delta potential, and our main question regarding this is one, to find how many number of bound states will be there. So we want to find how many number of bound states will be there in this attractive Dirac delta potential. So first thing that we are addressing is what are the number of bound state if a particle is encounters an attractive Dirac delta potential. So whenever you have this attractive potential, we place a negative. So this is something that we know. For example, one of the attractive potential is the gravitational potential. So you know the gravitational potential is minus gm upon small r. So you know there is a negative. So whenever you get a potential which is an attractive potential, so this is given by this. So what does it mean? It means that at x equal to 0, there is a Dirac delta potential given by minus of v naught Dirac of x. Now, let's say there's a particle. Let's consider particle of. Let us consider a particle of mass m, which faces this kind of potential. Okay, and let's say this it is subjected to a potential of the form given by here, subjected to a potential v as a function of x is equals to minus v naught, then Dirac of x. Okay, now you can understand that here this is a bound potential, isn't it? It is a bound potential, so there is a possibility that the particle may get bound, and that is what we are asking. We are asking what are the number of bound states. Okay, so we are asking the number of bound states. Another thing that I want to tell you is whenever you have this condition of boundedness, your energy is negative. The total energy remains negative. You can find it on your own end. Like whenever you consider the bound systems, so your total energy remains to be negative. Okay, the total energy remains to be negative. So most often I would address this in this fashion. So for example, I will write the magnitude of E is equals to minus of E, or simply your energy I will write as minus of E modulus. Okay, so most often I will use this kind of thing. So don't get confused. So basically, whenever you are writing your energy is negative, what does it imply? It implies that your modulus of E can be written as minus of E because your energy is already negative. So modulus of E is equal to minus of minus, so overall positive. Or you can write that total energy is equals to minus of modulus. For example, I'm saying my energy is 3 units. So it will be minus 3 units. What does that mean? 3 units means magnitude wise, I'm saying. So overall, because since it is negative, I will say negative and modulus. So overall, this is how I'm going to represent my energy, because energy for bounds, total energy for bound systems is negative. Since the system is bound, so total energy has to be negative. Now, how to proceed, how to find the total number of bound state? We use the Schrodinger equation. Schrodinger wave equation. So minus h square upon pi z d square psi upon dx square plus potential psi is equal to E psi. Okay. Now, you have to keep in mind that we are discussing right now the attractive Dirac delta potential. So what I would do is I would simply write here minus v naught Dirac of x psi of x minus E psi is equal to 0. So this is minus E psi is equal to 0. And here you have minus h ket square upon twice m. And then you have d square psi upon dx square. Okay. Now, let us try to solve this particular differential equation. So in order to solve this particular differential equation, what would we do? We'll simply multiply this with minus h ket square upon 2m. So you have d square upon dx square plus we have something called as v naught plus e, and then entire thing multiplied upon 2m upon h square psi is equal to 0. Understand that it is E is equals to what? It is equals to minus of E modulus. So I will represent all these things in this way. Okay. Okay. So this is it. So this is what I have written. Now, so you have to remember this particular fact. You don't have to forget this particular fact that your total energy is negative. So I will more often write E as minus of E modulus. Okay. So this you have to remember because at the end I'll do something from this. Okay. Now how to solve this particular problem? How to solve this particular problem? What you would do? Sorry, there is a Dirac function here. Okay. How to solve this particular problem? You already know that your wave function psi is continuous. This is something that you know from the physical realizability of Schrodinger wave equation. The, the solution to the Schrodinger wave equation, that is psi, it is physically realizable if psi is the conditions for the physical realizability of the wave function is one of them is that psi must be continuous. This is you already remember. Okay, now Dirac delta function is equals to 0 if x is not equal to 0 and it is equals to infinite if x is equal to 0. So now there's a problem at x equal to 0. So we already know that our wave function is continuous. So it is continuous, then it is continuous at x equal to 0 also. So rather than defining this Dirac delta function at x equal to 0, what we'll do, we'll go in the neighborhood of x equal to 0 and try to find the nature of the wave function. Okay, so let us try to find the nature of the wave function. So what do? We'll simply say that for all x not equal to 0, the Schrodinger wave equation can be written as d square psi upon dx square plus I think 2m. This Dirac delta function would become 0 because at x not equal to 0, this is 0. Forget about it. You have simply this h ket square psi is equal to 0. Is that clear to you? And already have told that this E is equals to what? E is equal to minus of E modulus. So what I would do is I would simply write it as in the next step d square psi upon dx square minus 2m E modulus upon h ket square psi is equal to 0. In fact, this particular expression, I will write as some k square. Okay, because this is m2. M is positive, E modulus is positive, 2 is positive, h ket square is positive. So now it can be written as k square. People often make mistake by writing this as k square because if this is k square, then E is already negative. So you have to counter it. So what I've done, I've simply written a negative mod of E. So now negative is outside. You have this entire term as your k square. And this k square is equals to what I'm writing here. So this k square is equals to 2m modulus of E upon h ket square. Is that clear to you? Or simply your k is equals to root over twice m modulus of E upon h ket square. Is that clear? Now, let us solve this particular differential equation. So, okay. So we are aware that this particular differential equation, the solutions will be of the form e to the power kx or e to the power minus kx. Okay, the solution will be of either of the form this e to the power kx and e to the power minus kx. Okay, there would be some normalizing constant that I will write later, but you have to understand that as x tends to infinity, this particular wave function will blow up, and as x tends to minus infinity, this particular wave function will blow up. So we'll construct this wave function in a manner that it satisfies the condition that your psi x should not be infinite value. So it should be some finite value. So again, physical realizability of a wave function physical realizability of the solution to the Schrodinger equation is invoked, and we know that your function should be finite. So this wave function should be finite. So if it has to represent something, then it has to be finite. So as x tends to infinity, this cannot be the wave function. X tends to minus infinity, this cannot be the wave function. The simplest solution will be e की power minus kx if x is greater than 0. And for all x less than 0, your wave function would be, let's say, b e की power of kx. Are you getting my point? Up till this point, is there any problem? See, as x tends to infinite, this particular wave function will blow up. So I cannot keep this in my solution as x is greater than 0, because if x is greater than 0 and e की power kx remains in the wave function, then this will blow up. And x tends to minus infinity. If this remains in our solution, this will blow up. Okay, you already can see that this k is positive. So this k is positive, don't worry about it. Okay, is that clear to you? Should I move ahead?
Yes.
Okay. Now, what you can do is, you already know that your wave function in any case is wave function is continuous. Okay, so since wave function is continuous, what can we do? We can simply find this a and b by finding the continuity by using the continuity of wave function. So by using the continuity of wave function, what we'll do, we'll see that your wave function should be continuous at x equal to 0. That implies as epsilon tends to 0, psi of 0 minus h should be equal to limit epsilon tends to 0, psi of 0 plus h, 0 plus epsilon, limit h tends to 0, limit epsilon tends to 0, psi of 0 plus epsilon. And in fact, it will be equal to psi at 0 also. However, you can see from differential equation, it is very difficult to find all these things, because see, at x equal to 0, your Dirac delta function would become infinite. So you cannot find it explicitly here. But overall, by the physical realizability, we know that your wave functions should be continuous. So I can write in this fashion. Is that clear? Now, as I go ahead, what I find is 0 minus epsilon suggests me that I have to go from to the left of x equal to 0. So this will be b e की power minus k epsilon should be equals to a e की power minus k epsilon. As epsilon tends to 0, this is 1. So this gives me condition that a should be equal to b. So what I would do, I would simply say psi x would be equals to what? I can reform my wave function as this. Okay, is that clear to you? Now, another thing, whenever we are doing this Schrodinger equation, whenever we are doing Dirac delta function, one of the best thing that I've told you is things remain the same when we do the integral part. So what I would do, I would again try to solve my differential equation. So d square psi upon dx square plus, remember this particular thing, okay, plus I think minus v naught, I think it was psi, and then it was e into psi. So I have done already, I've solved this particular expression already, and I've written it. I think I should write it all over again. Don't worry about it. So this will be d square psi upon dx square. This will come here. So this will be 2m upon h cut square. Then this minus will come here. So it will be minus e psi, and minus e psi will be mod of e, I think. I'm not wrong here. Okay, so instead of writing e, write minus of e mod, and it will come here. So it will become this. And I think this negative, which, so sorry, ek kaam karte na, pehle ek ek karke chalte hain. Let me write this. Otherwise, I'll get confused, and then one confusion will lead to another. So this will be minus v naught. Okay. Now you have to multiply this entire thing with minus 2m upon h cut square. So what it will give you? It will give you d square psi upon dx square minus 2m h cut square. Then you have, this is wrong. Okay, sorry. Okay, so this will be minus 2m upon h cut square. Then this will be modulus of e. Then this will be minus v naught Dirac of x. This is it. Okay, so now what we do, see, our Dirac delta function is situated at x equal to 0. So you have an attractive Dirac delta potential at x equal to 0. I'm just making an exaggerated kind of figure. It's not this way. It is actually a very narrower spike. So it is minus v naught Dirac. So what is the strategy is, see, you already know that if I integrate my function with, and there is a Dirac delta function here from minus infinite to infinite, it will filter out me the value of function at 0. Okay. So similarly, if I know that my Dirac delta function is situated at x equal to 0, so what I would do, classically, I would try to integrate in the regime minus epsilon to plus epsilon, and epsilon tends to 0, so that it encapsulates, so that it encompasses, or it involves this kind of potential, because otherwise this potential is 0 everywhere. So we are not worried. So what we want is, we want to see that what would be the what how would things behave in this region only, because finally whatever happens, the particle will get trapped in only this region, that is minus epsilon to epsilon, in this particular this narrower spike. So what I would do is, I would integrate, I would write this as 2, I would integrate my expression, your equation 2. So this is what we do when we are finding the when we find a Dirac delta potential. So integrate 2 from minus epsilon to plus epsilon. So what I would do, I would integrate it from minus epsilon to plus epsilon. So when I integrate a second order differential equations, it will come second order derivative, it will become first order derivative from minus epsilon to plus epsilon. Is that clear? Plus, second thing that needs to be seen is minus 2me mod upon h ket square psi. Okay, then this will be dx from minus epsilon to plus epsilon. And then there would be, I think, plus 2m h ket square integral from minus epsilon to plus epsilon v naught Dirac x dx is equals to 0. I think it is clear. So overall, I hope it is clear. So what happens, what can I say about this? So this is nothing but it is equals to the wave function's derivative, positive side derivative. That is, we want to find the derivative of the wave function on the right, and here we want to find the derivative of the wave function on the left. So what does it imply? It implies the right hand derivative, and it implies the left hand derivative of the wave function minus. Now just think about it. This is 2, this is m, this is e, this is h ket square. All these things are positive. So all these things are positive, as well as these are constant. So you can get rid of them by putting them outside this integral, and your psi is integrated in a very narrow regime, which is actually like minus epsilon to plus epsilon, and the limiting case epsilon tends to 0. Any wave function would become 0 only, because this is basic. Any wave function's integral would become 0 only. So basically, this is like integrating a function fx, and I'm saying that you are integrating from minus epsilon to plus epsilon. So basically, you are integrating close to 0. Overall, whatever and the answer comes. So let's say this integral is capital F. So it will become f epsilon minus f minus epsilon. And if epsilon tends to 0, this is like f0 minus f0. So overall, this particular term will become 0. This overall term, that is integral minus 2me mod h ket square psi dx from minus epsilon to plus epsilon. In the limiting case, epsilon tends to 0 would become 0. But this expression will not become 0, because now here in this particular case, you can see from minus epsilon to plus epsilon, there is a Dirac delta function. And we already know that from minus epsilon to plus epsilon, if we integrate this Dirac delta function, we'll get 1, because this area would come out as 1. Is that clear to you?
Yes.
Is that clear to you? Okay, so this is like 0. Now, overall, understand this represents the wave function to the right of 0. This represents the wave function to the left, and sorry, this represents the derivative of the wave function to the right, and this represents the derivative of the wave function to the left of 0. What does it imply? It implies that I have to find the derivative of the wave function at 0 minus epsilon. So 0 minus epsilon means what? We are at on the negative side of 0, or left hand side of the 0, and here we are on the right hand side of the 0, and the derivative of the wave function. And we already know to the left and right the definitions of the wave function. Rather, you can see this particular thing. If somebody asks you, how would this look like? How would this look like? So at times in examinations also, this has been asked quite a lot amount of times. Probably TFR also, they have asked this particular thing. So if I write this a e की power minus kx, and if I write a e की power kx, this is equivalent to writing e की power minus of k modulus of x. This is something that you can verify. So if x is greater than 0, then modulus of x is simply x. And if x is less than 0, then modulus of x is minus x. Overall, it will become a e ki power kx. So you can write in this fashion also. Okay, and somebody asks you, how would the wave function look like? So, or the graph of the wave function would look like. Somebody asks you, how would the graph of the wave function look like? So I'll make it here so that, okay, so I'll do it here somewhere. Okay. So how would that look like? I'm going to make a graph so that this helps you out. So what I would do is I would simply make certain dots, and you have to understand. So this is how your e ki power kx behaves. If k is positive, then e ki power kx behaves this way. And this is how e ki power minus kx behaves. So this is how e ki power minus kx behaves. So this is how e ki power kx behaves, and this is how e ki power minus kx behaves. Is that clear to you? Now, for all x greater than 0, your function is a e ki power minus kx. So I have to just trace this part, because for all x greater than 0, you have this thing. And this will never cut this x-axis. This will become asymptotic to x-axis. And for all x less than 0, I have only a e ki power kx. So I only plot this particular portion. Okay, so this will not be there, this will not be there. So you can expect a cusp over here. This is a cusp. So your function is non-differentiable at x equal to 0. So this is how your wave function would look like. So this particular wave function would look like this. And there would be a cusp at x equal to 0. So there would be a cusp at x equal to 0. Is that clear? Now we already know that to the right, you have the wave function a e ki power minus kx. And to the left, you have a e ki power kx. Okay, so to the right, find the derivative. The derivative will be equals to minus ka e ki power minus k epsilon. And to the left, you have a e ki power kx. So this will become k a e ki power k epsilon, k a e ki power k epsilon plus 2m. Where is this energy part? V naught upon h ket square. So there is a psi also here. Okay, that is what I was thinking. And when this is integrated, okay, sorry, my mistake. Again, I have done a mistake here. So this will be psi x. So this will become psi 0. Okay, now this will become psi 0. Sorry. So this will not become 1. So this will become psi 0 because psi x is multiplied with this Dirac delta function. V naught as a constant. So V naught will go outside. So psi x into Dirac delta function dx will give you psi 0 here. So there will be a psi 0 here equal to 0. Is that clear to you? Is that clear to you? ये चीज समझ में आई ऊपर चली गई है. My mistake. I made a mistake here somewhere. Okay. Now overall understand the point. That I told you that your wave function is continuous. So if you write psi 0, whether you write psi minus epsilon or you write psi plus epsilon, limit epsilon tends to 0, they mean one and the same thing. They mean one and the same thing. And if you see that this particular expression is nothing but it's a psi epsilon, this particular thing is nothing but it is equal to psi at minus epsilon. So basically, so you can clearly see that this is nothing but it is equals to minus 2k. I think there was a derivative somewhere. Okay, so if I say that I have to just write it all over again. So I'll write it not 2. I'll write minus 2k minus ka e ki power minus k epsilon. And I will write minus ka e ki power k epsilon. Then I will write 2m v naught h ket square. This I will write it as I think a e ki power k, and instead of 0 I will write, instead of x I will write 0. So this will become, I think 1. This will become 1. So forget about this. This a gets cancelled. Forget about this. So what you will get simply, and as epsilon tends to 0, this will become 1. This will become 1. So overall, entire thing in the first two part, I will write simply minus 2k plus 2mv naught upon h cat square is equal to 0. And what does it yield? What does it yields me? It yields me the value of k. And you know that k is related to your energy, total energy. Okay, so k is related to total energy, that we know already, that k is given, now here k is given by, I think, mv naught upon h cat square. And we already know that your k is nothing but it is equals to, I think, minus 2 me, or you can write eme modulus upon h cat square. So you can write k as this way, in this way. Further, what you can do is you can just replace these values. So I'll replace these values. 2me modulus upon h cat square is equals to minus mv naught upon h cat square. Have I made mistake? I think somewhere if k is this, so I'll write this. This was k square, I think. Okay, so this is k. K is 2me modulus upon h cat square, and this is mv naught upon h cat square. So this will give me 2me modulus upon h cat square is equals to m square. Then this is v naught square. Then this is h raised to power 4. And I think e modulus can be written as m v naught ka square upon twice h cat square. And since modulus is this, total energy was nothing but it was negative of this modulus. So total energy is minus mv naught square upon 2 h cat square. Is that clear to you? So the total energy of such a system is minus 2 mv naught upon 2 h cat square. Okay, so we have solved this particular differential equation. This particular differential equation has been solved, and you know that your total energy is 1. Only one such solution has occurred. So only one such solution has occurred. It implies that there is only a possibility of one bound state. So for example, when we were doing a one-dimensional potential well, you had this energy, one-dimensional potential, one-dimensional infinite potential well, then the energy was dependent on n, and it came like these. So there are infinite many possibilities of energies here. Here there is only one possibility of energy. So therefore there is only one bound state given by minus v naught ka square upon 2 h cat ka square. So this particular thing depends upon the magnitude of v naught. So this particular energy depends upon the depth of the potential. So depth तो हालांकि infinite हो जाएगी, but overall depends upon the magnitude of potential. Is that clear to you? So if I'm discussing a one-dimensional attractive Dirac delta potential, then you find that the number of bound states are 1. Is that clear to you? Is that clear to you? Okay. Okay. So now let us find. हाँ जी.
इंटरनेट चल गया था एक बार वो डेरिवेटिव से बता देंगे क्या?
ओके ओके ओके, चलो वापस समझा देते हैं, बस थोड़ी सी ग्लिचेस हो गई थी बीच में मुझसे भी. देखो फटाफट से पढ़ते हैं इसको. ठीक है, सो देखो attracted Dirac delta potential, we were discussing attracted Dirac delta potential, which suggests that the form of the Dirac delta function would be minus v naught Dirac of x. Okay, understand that I am discussing bound state, so the total energy of the system should be negative. So E should be less than 0, and therefore I have written modulus of E as minus E. So E is equal to minus of modulus of E. Now let us consider this particular particle which is subjected to a हाजी बोलो.
सर आपने यहाँ पे अगर मॉडुलस ई को माइनस मॉडुलस ई ले लिया तो फिर लास्ट में आप फिर से माइनस भी लगा रहे हैं.
मैं वहां तक आ जाऊँ, एक बार मैं पूरा पढ़ा, मैं एक बार रीट्रेट कर ना. सो देखो अगर ये दिस पर्टिकुलर डिफरेंशिएशन, आई होप टिल दिस पर्टिकुलर पॉइंट you should not have any problem, because see Dirac delta function is infinite at x equal to 0, and Dirac delta function is 0 if x is not equal to 0. So the maths wise, if you see that x equal to 0, there would be an infinite here. So this is very difficult. But physics wise, we know that the solution of the Schrodinger equation must be continuous. So in any case, this psi should be continuous. So we'll use this kind of thing we don't know about psi at x equal to 0, because right now, if you place at x equal to 0, this will become infinite. So what we'll use, we'll say that forget about it. Just find the solution for x not equal to 0. And what is the use of it? Because if we know the solution at x not equal to 0, we know the solution in the neighborhood of x equal to 0. So we can find the solution at x equal to 0 also, because our wave function is continuous. So what we'll do, we'll simply go by saying, let us not consider x equal to 0. And let's say for x not equal to 0, what will be the wave functions? Wave function would only have this 2me upon h ket square. And e is written as minus of modulus of e. I have replaced it all over here. And I have written the wave function as a e ki power minus kx for all x greater than 0, and for all x less than 0, I have written b e ki power kx, because if it contains a e ki power minus kx term, then this will become infinite. And if this particular portion contains a term e ki power kx, then this will become infinite. So I've not used those terms. So according to the boundary conditions that my wave function should be finite, so I have done this particular, I have written the wave function in this particular format. Further, the continuity conditions give me a is equal to b. Okay. Now you see, what is good about Dirac delta function? हिंदी में बोले तो बाल की खाल निकालने का मतलब समझ लो. What it would do if I try to integrate it? So what it will become? So if I integrate this with respect to x from minus epsilon to plus epsilon, this will give you d psi upon dx from minus epsilon to plus epsilon. This particular expression, that is minus 2m upon h cut square e modulus into psi dx from minus epsilon to plus epsilon, this will become 0. See, because this is constant, forget about this. अंदर क्या रह गया? सिर्फ psi dx ही रह गया. So if you integrate psi dx from minus epsilon to plus epsilon, given that epsilon tending to 0, so basically this will become 0, because any integrable function, let's say if I have written fx, if I say that my fx is integrable and it becomes capital F, then capital F at epsilon minus capital F at minus epsilon, and epsilon tends to 0, this will become 0. So in any case, this will become 0. But in this particular thing will not become 0, because there is a Dirac delta function associated with it. So Dirac delta function would actually filter out the value of the psi at x equal to 0, because it is associated with psi x into Dirac delta x. So what you do from minus epsilon to plus epsilon, if you integrate it, v naught is a constant, forget about it, this will become psi 0 here. So this will become psi 0. तो हिंदी में बोले तो it will, ये बाल की खाल निकालेगा, ये नहीं निकालेगा. This particular function is not worried. ये कहेगा integrate psi dx from minus epsilon to plus epsilon, keep the upper limit, lower limit, epsilon tending to 0, overall it will become 0. But ये बाल की खाल निकालेगा. It will say no. My entire contribution is here. So it will give me psi 0. Okay. Now understand the fact, what does psi dash epsilon mean? It means I have to find the derivative of my wave function to the right. I have to find the derivative of the wave function to the left. So this is what I have done. Derivative, the wave function to the right is a e ki power minus kx, and derivative to, the wave function to the right is a e ki power minus kx, and the wave function to the left is a e ki power kx. And if I differentiate it, what I would get simply minus ka e ki power minus k epsilon, and to the left I will get minus ka, because there is a negative here, so minus ka e ki power k epsilon. Understand, this is psi 0. Whether you write psi 0, whether you write psi minus epsilon, whether you write psi plus epsilon, they mean one and the same thing. So basically you can cancel them all, and you will get minus 2k plus 2m v naught upon h cut square. And k is equals to what? It will give you k is equals to mv naught upon h cut square. You already know that your k is root over 2me modulus upon h cut square. I think this was it. I think I forgot, right? This was thing. This is what I wrote. I think somewhere here. If you remember, this is so, and this is what I will use here. Okay. So this k is equals to root over 2me mod upon h cut square. So I will write. I will square them up. So what will be the value? 2me mod upon h cut square is m square v naught square upon h ki power 4. So modulus of e, this is the magnitude of the total energy. This is mv naught square upon 2h cut square. So if somebody is asked you the magnitude, this is the answer. And if somebody says what will be the value of the energy, so I've already told you that what the value of the energy is. Since modulus of E is minus E, it will give you minus mv naught square upon 2h cut square. What actually confuses many people is, either in 12th class, some maths teacher would have told them कि जैसी mod हटता है वैसे plus minus आ जाता है. This is I don't know why this is taught like this. I don't know why, but overall understand what my understanding to this modulus function is simply this. देखो, मॉडुलस का मतलब क्या है? इट सेज कि तुम्हें एब्सोल्यूट वैल्यू निकालनी है, एब्सोल्यूट मतलब मैग्नीट्यूड निकालना। तो अगर पॉजिटिव है तो जो अंदर बोल रहे हो वही रिटर्न करो। लेट्स से मैं भरत से बोलता हूँ व्हाट विल बी द एब्सोल्यूट वैल्यू ऑफ 2, तो ही विल से 2। मैं अल्पना से बोलता हूँ व्हाट इज द एब्सोल्यूट वैल्यू ऑफ -2, तो वो बोलेगी 2। मैं बोलूंगा नहीं, माइनस ऑफ -2, दिस इज 2। So overall, understand this is the definition of the modulus. So modulus of E, since energy is negative, can be written as minus of E because energy negative है ना। अब नेगेटिव एनर्जी का मॉडुलस क्या होगा? इट विल बी पॉजिटिव ओनली। तो उसको बोलने का तरीका क्या है? इफ यू वांट टू गेट रिड ऑफ दिस, यू विल से modulus of E is nothing but minus of E. So E is equal to minus mv naught square upon 2h square, which should be the case. Energy should be negative because it is a bound system. So there is only one possibility of energy. So therefore, there is only one bound state. There is only one bound state. Is that clear to you? Okay.
यस सर।
Now, what teacher could have, what I don't know. Sometimes students also take some wrong messages or some wrong takeaways. What teacher wants to say in standard 11th is, let's say modulus of x is 9, and then he says x equals to plus minus 9, absolutely fine. What he wants to suggest is कि modulus हटने से plus minus आ जाता है. What does it imply? He wants to say whether you take the modulus of 9 or you take a modulus of -9, this is one and the same thing. But otherwise, modulus is supposedly this. Right? It is supposed to be defined like this. What he wants to say in an equation is not what modulus function is all about. Well, you cannot say कि modulus of x is plus minus x. No, either it is x or either it is equal to minus x. Okay, it cannot be plus minus x together. However, this particular solution to this equation is fine. I mean, if you are understanding what we probably your standard 12 teacher wants to say, he wants to make your understanding in this fashion. कि मॉडुलस हटाया तो प्लस माइनस आएगा, मतलब you take a modulus of 9 or you take a modulus of -9, they mean one and the same thing. So we'll continue it in the next lecture, but I'll write what is my next sort of question with this. So you have to find me the you can say probability of particle in the region. Let's say if we were doing one-dimensional well now, so -a2 plus a. So just find me the probability of finding the particle in the region -a2 plus a, and given that your Dirac delta potential is situated at x equal to 0 only. So the problem is same. You have to just find me the probability of finding the particle from -a2 plus a. So find me the probability of finding the particle from -a2 plus a. So what we have to do first is we have to normalize and find this a. Otherwise, we'll not be able to come to the right conclusion. So first, writing this, so you just solve in the break. First thing, normalize the wave function so that you can find this a. So you'll find a, and then you have to find the probability of finding the particle in the region from -a to plus a. Okay, so I'll do it for you. So if I normalize from -infinity to +infinite, psi mod square dx should be equals to what, 1. So this will give me from -infinite, I think कहाँ गया वो, from 0, array square second. So this will be, I think I will write the wave function here. So you just solve it in the meantime because I have less amount of time left with me. So I'll write it here, a e की power kx if I think x was less than 0, and a e की power minus kx if x is greater. Just find this particular, solve this particular expression and find a in the meantime. So from -infinite to +0, from 0. Just do it.